Hello, everybody. This is Steve Tockey from Construx Software, Principal Consultant. With me in the background are Eric and Jesse. They will be fielding questions. In case you have any, feel free to pop a question into the chat, and they'll take care of them if they can. Otherwise, they'll queue them up for me at the end of the presentation. So let's get going. Top 5 challenges in software development. Legal stuff, fine. The overall outline, experience shows, data shows, mainstream software projects don't often perform very well. We'll look at some data around that. We'll go through some what I consider to be the top 5 root causes of that poor project performance. And then at least at a high level, I want to talk about a get well plan so that we can do better in the future. So the data we have about mainstream software projects performing poorly is, for example, 18% of projects fail to deliver any usable software at all. In other words, the project is canceled before any software of any use is actually produced. Of the projects that do deliver, they average about 42% late, they average 35% over budget, and they average 25% under scope, and there's an abundance of delivered defects along the way. Now, I couldn't find any world statistics, but statistics in the US for 2019 are that $340 billion got spent on software development in the US last year. Now, 18% of that would be $61 billion in cancellations. Now, keep in mind that this is a rough order of magnitude, back of the envelope kind of analysis here. The real numbers are probably somewhat different, but this is going to at least put us into the ballpark. So out of the $340 billion, if 18% of projects fail to deliver any usable software at all, then we're talking on the order of $61 billion lost in the canceled projects. However, I do need to point out 2 things here. One is that we know from past history that it's the larger projects that tend to fail more often than the smaller projects. And so one would expect that if 18% of projects by population fail, but that larger projects fail more often than smaller projects, that more than 18% of the budget would need to be allocated to the failed projects. And the other thing is that when canceled projects do get canceled, they don't usually get canceled at the point that they've used up their budget. The history shows that they usually get canceled when they've more than doubled or approximately doubled their budget. So we're looking at 61 billion in canceled projects alone being an absolute bare minimum. The real number must be higher than that. Now, from the remainder, if you take off about 35% of that because those projects overran their budget, and then if you take another 25% because of the projects overran scope, then we're looking at, in terms of, again, an order of magnitude, a back of the envelope calculation, that the people who were paying for the software expected to pay only about $166 billion for the functionality that actually got delivered. For what they got out of the money they spent, they expected to pay about half of what they actually paid. And so instead of just saying 42% late, 35% over budget, et cetera, I'm trying to cast this in terms of a true economic valuation that gets at the importance of having to pay attention to this. Now, in terms of why this is happening, now I have real data that supports the first 2, and my 43 years of professional experience it suggests the other 3, but I don't really have legitimate documented data, but work with me on this one. Okay, the data supports number 1 reason, vague, ambiguous, incomplete requirements. Now, where that data comes from is that I've done a lot of classes with organizations over the last 20 some odd years. And for most of the classes, we start off with a discussion of what are your challenges. Now, I am not prompting them for what their challenges are. We just build a list of the things that challenge the organization. And then we have them rank order the list of challenges. And the point that I'm making here is that about 44% of the time, their ranking of their self-identified challenges is some manifestation of vague, ambiguous, and incomplete requirements. So nearly half the time, people are given the opportunity to say what their number one challenge is. They would say that it's vague, ambiguous, incomplete requirements. Inadequate project management comes up by the same data, by the same mechanism, about, I think, 37% of the time. We'll look at more detail at each of these as we go along. But just to say how important they are, what the data is, this is where we're starting with. Now, again, I don't have actual survey kinds of data for the other three. These are just based on my professional experience over the past 40 some odd years. Uncontrolled design and code complexity, and overdependence on testing, more detail on that later, and this whole idea of self-documenting code being a myth. And I need to point out that self-documenting code being a myth is not really so much of an initial development problem. The issue here is a long-term maintenance problem. And since the data shows us that about 80% of what gets spent on software over a year is maintaining existing code rather than building new code from the ground up, that this actually does turn out to be quite a serious problem. Okay, and so what I'd like you to do is kind of think in the background about whether these are your top five. If they are, great. If they're not your top five, it would be interesting to hear what you think your top five are. You can send them in with the chat. Okay. So let's get into more detail about what these challenges are. And so number one, vague, ambiguous, incomplete requirements. I argue that this is a direct result of using natural language as a means to try and communicate requirements. Natural languages like English, like French, German, Chinese, etc., that all of these languages have built-in ambiguity. Different words in the language often have the same meaning, and the same word in that language can often have very different meanings. And this can cause some serious problems, as we'll see in just a moment. Now, verbose-ness, the bottom line here is that if you want to say things and you want to say something precisely, it just takes too many words to give the level of precision that's really needed when we're talking about something like software requirements. Built-in ambiguity in natural languages can actually be kind of entertaining in some cases. My mom spent her entire professional career in the newspaper industry, and so she happened to stumble across a very interesting book. I don't have a copy of it with me right now, unfortunately, but the title of the book is Red Tape Holds Up New Bridge, and the whole gist of the book is all about newspaper headlines that went wrong for some interesting reason. And the interesting reason in most cases turned out to be due to ambiguity in these natural languages. So for example, youths steal funds for charity. I mean, I think what the headline writer meant to say was rather obvious, but it does cause one to think of maybe Robin Hood happening here. Sisters reunited after 18 years in checkout line at supermarket. I mean, isn't that quite a long time to spend in the checkout line? Don't they open up another cashier if people have to wait more than 15 minutes or so? Large church plans collapse. Police discover crack in Australia. Now, yeah, you can figure out what they meant eventually, but it's certainly interesting to look at the difference between what the newspaper headline writer had intended and what are certainly valid and funny interpretations of these, again, these headlines on the newspaper articles. Now, as I said, this can be mildly entertaining when what we're talking about is everyday conversation, newspaper headlines, et cetera, et cetera. However, when we get into software and specifically software requirements, this can actually be quite deadly. So what I'm showing you here actually is a real requirement from a real software project that was with an organization I was working with in Paris. This particular organization builds devices that inspect pipes in chemical plants. And so every so often you have to shut down the chemical plant and you send this device through the piping network in the chemical plant. And it's trying to find problems in the chemical plant before you have a leak in the pipe causing a hazardous material spill. And so the as stated requirement was, quote, the system shall detect a 1/4 inch defect in a pipe section. Now, clearly the person who stated that requirement had something in mind. However, when we look at ambiguity, some interesting things happen. And so the question becomes, let's take first a look at the word detect. What might the word detect mean? And so the issue here is there are actually many possible interpretations of just this one word detect. And so possible interpretations would include things like measure, how about record, how about locate, how about report, and how about any combination of those 4 possibilities. And so that essentially gives us on the order of 16 possible different valid interpretations of just that one word alone. Now let's move on to the word A. What could A mean? It could mean 1. It means just go find one, and when you find one, stop. Or it could mean find some. It's okay that you don't find all of them, but as least as you find some of them, that's good enough. And then the third interpretation here is no, you need to find all of them. And so 3 possible interpretations of the word A multiplied by the about 16 different possibilities for the word detect, and we're at 48 unique interpretations, different interpretations of this one requirement statement alone. And then we move on to the word 1/4 inch. And now, does that mean as small as, or does that mean as big as, or does that mean exactly that size, no bigger, no smaller? So multiply the 48 other interpretations by another 3, and now the list of possible valid interpretations grows even more. And then we move on to the word defect. Does that mean a hole? Does that mean a dent? Does that mean a bulge? Does that mean a crease? Does it mean corrosion? Does it mean some combination of those? And so because I have 5 possibilities here in any combination, we pick up another 32 unique interpretations here. And then finally, we move on to the issue of pipe section. Is a pipe section an isolated volume when all the valves are closed? Is it the straight line segments in the piping network? Is it everything between the welds and the joints? Or is it some fixed length like 10 meters of pipe? And so the bottom line in all of this is that there turn out to be actually, for this one requirement statement alone, 9,000 at least, I should point out, there could possibly be more, at least 9,126 unique interpretations, valid interpretations of this one requirement statement alone. Now, the whole problem is here that if there is some number n, whatever n is, valid interpretations of some requirement statement, the question becomes, what's the probability that any 2 people have exactly the same interpretation of that one statement? And I think from just purely a statistical standpoint, you have to say the probability of the 2 people having exactly the same interpretation is on the order of 1 over n, which then means that the probability of different interpretations would be n minus 1 over n, which then leads to the idea that even if n is small, say 3 or 4, the probability is quite high that there's a misinterpretation. Now, when the n is 9,126 or larger, I think you have to admit that it's virtually impossible for the people to have the same interpretation. And this is exactly what happened on this project. The developer's interpretation of this one statement was radically different than the business's interpretation. Developer said, yeah, we got it. They went out, 4 developers spent about 1.5 years writing code to their interpretation, which turned out to be completely a wrong interpretation. And so when this was demoed to the business says, you have got to be kidding. That is not what we meant when we said detect. That's not what we meant when we said A, et cetera, et cetera. And the bottom line was because their software architecture was fundamentally based on their particular interpretation, they had to scrap the entire code base of 4 people, 1.5 years, and start again from scratch. So it was a very expensive misinterpretation in the end. If you want to be precise in natural languages, it's very difficult, as I was saying. The natural languages are inherently very verbose. Professional experience, I had to build a custom house. It's a very long story. We should probably not go into it here, but long story short, building a custom house involved things like where do doors go and which way do they swing. And so in order to say in English, specify the behavior of a particular door that was really a door in this house, the main floor guest bathroom shall have a door. That door shall be a right-hand door. That right-hand door shall be oriented so that the hinges are on the south side of the door frame. Now notice it took me literally half a paragraph to say what in a drawing on the house blueprints was literally just a single line and an arc. And if I could show you the house drawings, because I still have them, there are 9 pages of engineering drawings on the house. And the challenge would be to take the entire information content that's on these 9 pages of engineering drawings and translate that to a natural language, a set of natural language statements on the order of Steve's house shall, Steve's house shall, Steve's house shall, Steve's house shall. And the 9 pages of engineering drawings, if you could not use drawings to communicate, you could only use natural language to communicate. I think that any reasonable estimate would have to involve hundreds, if not thousands of pages of Steve's house shall, Steve's house shall, Steve's house shall, in order to carry the same information content that's in these mere 9 pages of drawings. But then you run into the problem of if there really are hundreds or thousands of pages of information content, now the question is, how do you know that everything's complete? How do you know that everything's consistent? Something said near the bottom of page 246 could easily be contradictory to something that was said on the top of page 921, for example, and how would you be able to figure that out? So in the end, the people who design and build houses gave up trying to describe them in natural language over 100 years ago. What makes you think you can successfully describe something that's orders of magnitude more complex using natural language? I mean, think about it. How complex is a house? Houses are fairly easy to understand when you get down and think about it. But think about the complexity that's involved in the kind of software systems that you work with every day. These are clearly orders of magnitude more conceptually complex than than a standard house. And so, as I said, the people who tried to describe houses gave up using natural languages more than a century ago. Why do we think that we can continue to, in the software realm, describe things adequately that are orders of magnitude more complex while still using a natural language? It puzzles me. I will go on to say that in my experience, what most people claim to be the requirements changing turns out actually, in my experience, to not be requirements change. The issue here is that if you look at what the business wanted when we started the project, and if you look at what the business wants today, most likely most of the time. What the business wants today is usually what they wanted at the beginning of the project, but the problem was that we didn't understand what we interpreted what they wanted at the beginning of the project was different than what they actually wanted. And so what we're doing is accusing them of changing their mind when in fact they never changed their mind. It was not the requirements were changing, they were only being clarified. And so because of the vagueness and the ambiguity and because of the incompleteness, all driven by use of natural language, it's very easy to put the blame on them for saying, oh, you're constantly changing your mind, when in fact the problem is not there. The problem is how we're doing requirements, not leading us to what the customer really wanted when we were having initial conversations with them. Now, in terms of inadequate project management, this is just a partial laundry list of the kind of things that I tend to see. Insufficient goal alignment. This includes constantly changing priorities. How many of you on your projects are complaining that, well, today the hot priority is this and tomorrow the hot priority will be whatever, based on some manager's phone call with some irate customer? The priorities are constantly changing. Inadequate planning of the projects. Things are left out of the plans, things were unknown. Overly optimistic estimation. There was no way that we could get this amount of work done in what the estimate was claimed that it could be done in. Failure to acknowledge inherent uncertainty. That's an entirely different topic. I would like to refer you to Steve McConnell's recent Lunch and Learn on the whole history and the current status of the cone of uncertainty. This goes into much more useful detail on this particular topic that we don't have time to go into here. Lack of risk management, lack of active risk management. Inadequate project tracking, which in my experience includes weak supplier or subcontractor oversight. I'm calling this out because anytime your project has a dependency on some other project, if that project doesn't deliver on time, on budget, with appropriate quality, everything, et cetera, then it puts your project at risk. But quite often, our project just assumes they will deliver, only to be surprised later on because we weren't paying attention to their inability to deliver and how that impacts our ability to deliver. Insufficient change control, noisy, crowded facilities. These are all just examples of the kind of things that we tend to run into that would fit under the general topic of inadequate project management. When we move on to the topic of uncontrolled design and code complexity, I think people will hopefully tend to agree that the complexity in the code base is just constantly growing. It's not being controlled. And it gets to the point where people just can't understand how things work and how things all fit together. Now, I want to go into a little bit more detail here with the notion of syntactic complexity. What I mean here is that there are some software structural complexity measures that have been known to be correlated with increase in things that we care about not happening in software, specifically defects. And so cyclomatic complexity, if you just count the number of decisions that are in some section of code, that at the function level, not at the entire code base level, but if you do the correlation at the single function level, there are clear correlations between, as the number of decisions, the cyclomatic complexity in a single function increases, the density of defects in that function increases along with it. And data shows fairly clearly that for cyclomatic complexities of 5 or less, compared to cyclomatic complexities of 15 or greater, that the density of defects on a per line of code basis is about 13.4 times greater. And so you're seeing, for going to cyclomatic complexity 5 or less to cyclomatic complexity 15 or greater, more than an order of magnitude difference in the density of defects in that section of code. Depth of decision nesting, not just looking at having decisions, but the degree of dependence between the decisions. So having an if statement embedded in an if statement, embedded in an if statement, embedded in an if statement. And some research has shown that as the depth of decision nesting increases, again, the density of defects increases along with it. Number of parameters on a function. Some interesting research out of the Netherlands shows that as the number of parameters increases, it also causes increases in the defect density. And fan out. If I have a function, how many other functions are called by that function? And Bob Grady at Hewlett Packard has been had done some research on that, showing fan out also. As that increases, defect density increases. Now, the point in all of this is that if I pick on just, for example, cyclomatic complexity, showing you that I've got an order of magnitude increase in defect density with cyclomatic complexity over 15 versus under 15, that if you do a cyclomatic complexity survey of a typical code base, that we will routinely find cyclomatic complexities in the 70 or 80 plus range. And I've actually seen code where the cyclomatic complexity was on the order of 2,400 and change in a single function. That was about 3,400 lines of code. And so what we're looking at here is within a single 3,400 line of code function, which is already a problem. 2 out of every 3 lines of code in that function have a decision in them. And that's clearly, we've got something out of hand here. Semantic complexity, I want to contrast with syntactic complexity. Syntactic complexity is purely structural. It doesn't matter at all what the code does. It only matters what the code looks like. Semantic complexity, I don't care what the code looks like. What I care is what the code does. And here I'm looking at things like abstraction, poor abstraction. I'm looking at weak or non-existent encapsulation. I'm looking at low cohesion, high coupling. I'm looking at things like reactive, not proactive product family development, just driving the code complexity through the roof. And these are all very, very common things that we see when we survey existing code bases in existing organizations. Hardly anybody says that their product code base is in any kind of good shape at all from a complexity perspective. Moving on to the next challenge, overdependence on testing. It's been well known for many, many years, dating back to the 1970s, that the earlier the mistake was made, the later the mistake was found and fixed, the exponentially more expensive it is to fix the mistake. And this is primarily driven by at least 2 reasons. One of them is the consequential decisions. A requirement is a decision that's imposed by the business stakeholders. Okay, fine. But based on that one requirement statement, the designer developer will make several design decisions, and as a consequence of each of those design decisions, there are several more coding decisions. And so you see an exponential growth in the number of decisions. And so if the earlier decision changed, it has an exponential cascading effect on later decisions that will likely have to be changed to bring them into sync with the earlier change. So that's one thing that's driving this. And the other thing that drives this is simply familiarity. Wall clock time or calendar time. The basic idea being that if we are familiar with this section of the system because we've been working with it recently, that's fine. But the longer the time passes on the calendar or on the clock between when we last look at it, we forget more of the larger context. It takes longer to go back and find. So again, the combination of those 2 drives this exponential increase in cost between when some mistake was originally made and when that particular mistake is found, and now we have to go fix it. And so hopefully what you're seeing here out of this is that the, in general, most expensive kind of defect that we're ever going to have to worry about dealing with would be a defect in a requirement that was not discovered until the customers were using the system and saying, this is not what we meant. That would typically be the most expensive kind of defect to be wrestling with. Okay, fine. But now, if you look at the defects that are in a typical defect tracking system and you do what's known as a defect causal analysis, you say, interesting, when was this mistake made? That you tend to get data along these lines, that the root cause, the when did we make this mistake, 56% of the time, it was a misinterpreted, missing, invalid, ambiguous, etc. requirement. That's 56% of the time. So more than half the time, it's a problem in the requirements. 27% of the time, it's a design problem. Wrong algorithm, wrong data structure. We understood the requirement, but that was not an appropriate solution to that requirement. Only 7% of the time is it really a code injected problem. And what I mean here is that if you had a single equal rather than a double equal sign in an if statement in C or C++ or something like that, semicolon was in the wrong place, the else is not tied to the right if then, those would be examples of coding injected defects, and those are only 7% of the time. Now, the 10% other category is there for organizations that use their defect tracking system to track defects beyond just requirements design code. Let's just say that, for example, we did a review of a test plan and we found some problems in the test plan. Some organizations would log the defects found in the test plan into their defect tracking system. And so that's what that 10% other category is. And so now if you look at the mere fact that 56% requirements injected, 27% design injected, that this is telling us that 83% of the defects are injected before the code corresponding to those defects is actually written. And so if you combine this idea of where are we actually making the mistakes with the idea of how expensive is it to fix the mistakes based on where we made the mistakes, that you see that in a typical organization, you don't even start to look for defects until after the code has been written. Whereas the majority of the defects, 83% of the defects, were injected before we even started writing the code. And so clearly this is going to be driving the cost of those defects through the roof. Which leads to, if I was the manager of an organization and I wanted to measure things in the organization, if I could only measure one thing, the one thing that I would want to measure first is this measure called rework percentage. Now, let me explain. So IEEE Computer Society has a dictionary of software engineering terminology, and they talk about three different categories of software maintenance. One category is adaptive maintenance, and that's where I'm, for example, porting the code from platform A to platform B. That would be adaptive maintenance. Perfective maintenance is where I'm taking something and I'm making it better. I'm tuning performance, I'm adding new functionality, etc. Again, that's perfective maintenance. The third category is corrective maintenance. I'm fixing something that is broken. And so the point that I need to make here is when I use the term rework, I am focusing only on corrective maintenance. We are ignoring explicitly the adaptive maintenance. We are ignoring the perfective maintenance. We are focusing purely on the corrective maintenance. Now, what I want to do is calculate how much of the project's time is being spent on this corrective maintenance, and then look at the total amount of time that was spent on the project. And if I divide the corrective maintenance time by the overall time, that gives me this R%, this rework number. And so take a moment, if you will, and just think about in your organization, if we focus in purely on the corrective maintenance that's going on in our project team, what percent of the overall work is that? And the most common number I'm getting back in asking people informally, the most common number I'm getting back is somewhere in the neighborhood of 50%. So about half of our capacity to do work is being spent on this corrective maintenance per the IEEE definition. Now, this is actually a measurable phenomenon. We don't have time to go into it right now, but we can instrument your defect tracking system, or we can instrument the product backlog, the sprint backlog on Agile projects. And it's actually quite easy and quite straightforward to really measure this precisely in an organization. Now, we've actually measured it, and that's the point. We've actually measured it in 5 different organizations of varying sizes, and here are the as measured results. A 350 developer organization measured 57%. A 50 developer organization measured 59%, 125 developer organization 63%, 100 developer organization 65%, 150 developers 67%. This was the as measured corrective maintenance as a function of total labor hours spent in those organizations. Now, if what you do here is calculate a weighted average, it comes out to be about 62%. So think about that. In these organizations, 62 of every 100 labor hours that the organization is spending is fixing things that were broken earlier. And so more than half of your capacity to do work is being chewed up in rework percentage. And so the quote here is very, very true. Rework is not only the single largest driver of cost and schedule on a typical software project, it's bigger than all other cost and schedule drivers combined. If the cost and schedule drivers are doing requirements work and doing design work and doing coding work and doing testing work, if those are the drivers, you have to consider that rework also being a driver, that if rework is 62%, that the other drivers combined cannot be any greater than 38%. And so if you care about productivity in your organization, the number one target of opportunity here is to be looking at what are we doing about rework, because it is the single largest driver of cost and schedule in a typical organization. Now, we normally think about defects as relating to the quality of the product, but a often misunderstood dimension is defects and the relationship to quality of the process. And I think these two quotes are actually quite appropriate quotes. Martin Thomas, a professional acquaintance of mine, an engineer wants their system to be fit for purpose and chooses methods, tools, and components that are expected to achieve fitness for purpose. It's poor engineering to have a system fail in testing, partly because it puts the budget and schedule at risk, but mainly because it reveals that the chosen methods, tools, or components have not delivered a system of the required quality, and that raises questions about the quality of the development process. Paraphrasing Tony Hoare, the real value of test is not that they detect defects in the code, but they detect inadequacies in the methods, concentration, and skills of those who design and produce the code. So again, defects are not just about product quality. They tell us quite a lot about the quality of the process that's being used to develop the product. Self-documenting code is a myth, and so let me just explain what I mean here. You can go grab any arbitrary chunk of code and you can analyze the code. You can hand execute the code. You can execute the code in a debugger. You can do whatever you want with the code, and you can figure out what the code does. That's not a problem, figuring out what the code does. The question is, what is the code intended to do? Is the code doing what the code was intended to do? What is the intent of the code? And while most people call it a bug, I hate that term. You'll notice that I tend to use the word defect, not bug, for reasons we could talk about offline. But what you call a bug, what I call a defect, is merely a difference between intent and what the code does. The code was intended to do X. The code doesn't do X. The code does Y. That difference between X and Y is in fact the bug that we're looking at. What is the intent? What does it actually do? Any difference between actually do and intent is a bug, is a defect. And so where is it stated what the code was intended to do? It's clearly not stated in the code. And so now you have the problem. I see the code, I see what it does. What is the code intended to do? So that's problem number one. Now, problem number two, you're looking at this code. Why does this code look the way this code does look? Does this code have to look this way, or does this code just happen to look this way? And this has to be, happens to be. How can I tell just by looking at some code that it has to be like this, or it just happens to be like this? And the answer is simply that you can't. Now, you may be able to get some of this into a method, into a class, but as the size of the code base increases beyond a couple of thousand lines of code, when you get up to 20, 50, 100, 500,000, millions of lines of code bases, there is no way on planet Earth that you're ever going to be able to capture intent and all of this why in the code itself. It's not going to work. These emergent properties about why the code looks the way it does transcend the code structure in a way that it's just impossible to capture it as part of the code structure itself. And so I want to start now looking into a get well plan, at least at a high level. There's many gory details that fit under this, but at least to get us pointed in the right direction for right now. And so remember that our number one challenge is vague, ambiguous, incomplete requirements directly as a result of using natural language in an attempt to communicate the requirements. And so I'll say that you have pretty much two options here. Acceptance test-driven development, for those that are familiar with the concept. This is where we agree on a set of demonstration test cases. We agree on a set of compliance test cases that the code needs to pass before any developer goes off and writes the code. Again, for a user story as an example, we will agree on the set of test cases that the code needs to pass to agree that the code meets the intent of that user story before anybody goes off and does serious development on that story. And so while it's normally interpreted a test-driven development to be a testing technique, it's actually not so much a testing technique as a requirement specification technique. Each one of those acceptance test cases is in fact a requirement. It just happens to be a requirement that's written in test case language, not in a natural language like English or German or Korean or what have you. And everybody should understand that test case language is pretty much by definition unambiguous. When given input that looks like this, the system, we expect the code to produce output that looks like that. That's the general structure of a test case. Notice that that's just a minor tweak from the idea that when given input that looks like this, the system shall produce output that looks like that. We're just changing the we expect to see to shall produce, and instantly what we thought was a test case is actually a requirement. And so all of those acceptance test cases end up being proxies for the requirements. They're just happening to be written in test case language, which is unambiguous, not English, which is ambiguous. Now, This does solve the incomplete or the ambiguity problem. Unfortunately, it doesn't solve the incompleteness problem. We have to do some other things like introduce some issues about test coverage criteria in that case. But again, more detail for a later time. The alternative is much like the house drawings, the blueprints for the house. Remember how the people who designed and built houses gave up trying to use natural language to describe houses. They came up with a blueprinting language. Electrical engineers use circuit diagrams. Things that are very complex tend to be not describable in English. So some kind of specification language. It may be a formal language, it may be a semi-formal language. But various incarnations of UML, for example, can be applied very productively to solve requirements problems. But again, that's a much deeper topic for a separate time. Improve your project management. Focus on project management activities that enhance goal alignment, that enhance better planning, that are around better estimation, that are around dealing with the uncertainty in projects that we know is there. There's a whole laundry list of things that we can do to shore up project management. Number three, since the challenge here is unmanaged design and code complexity, the Get Well plan is to manage the design and the complexity. But if you can't measure it, you can't manage it. And so let's start measuring design and code complexity and controlling the design and code complexity. I see many organizations have adopted tools like SonarQube and FXCop and etc. There's a ton of tools out there. So they'll run the code through the tool and they'll get the report out of the tool, but they won't act on it. And so why bother measuring if you're not going to act on it? Unless you say cyclomatic complexities over some level are not allowed, depth of decision nesting over some level are not allowed, that number of parameters over some level is not allowed. I've actually seen code where a single function had 58 parameters. And clearly this is ridiculous. And again, we routinely see functions in the cyclomatic complexity range of 150, 160. That's fairly routine. And over 60, 70, or 80, I'm willing to bet lots of money that it's trivial to find these in any significant code base because we're not measuring and because we're not controlling. Number four, instead of depending on testing to be finding defects, depend on other forms of quality to be identifying and, more importantly, avoiding defects in the first place. By appropriate use of templates and checklists and by appropriate use of early reviews, we can actually find defects early, get them fixed early while they're much less expensive to fix, and we can actually avoid defects in the first place. If the template tells us that we need to address this issue, then we're less likely to forget to address the issue. If the checklist tells us, make sure that you've solved that problem before you move on, then these are ways of avoiding the defects in the first place. Again, to battle this idea of, well, my code is self-documenting, and my response is, well, if it's over a couple of thousand lines, it cannot be self-documenting. The last thing you want to do is don't not document. Again, this apologies for the double negative, but yes, I'll admit that traditionally how we've documented has been a massive waste of time. But that's not documentation's fault. That's our approach to the documentation. And so don't, as they say, throw the baby out with the bathwater. Don't just throw away all documentation altogether. Let's focus on value-added documentation. Let's focus on documentation that adds value, that's not a waste of time. Part of the mentality here is to not document for the sake of development. That's what I see quite often, that any documentation is there for the sake of development. But again, that's only 20% of the money that's being spent in software organizations. 80% of the money is spent maintaining existing code. So don't document for the sake of developing it and then throw the documentation away and let it go stale. Document for the sake of ongoing maintenance. The people that are going to maintain the system over time need to know what the intent of the code is, and that's what requirements documentation should all be about. Document requirements to expose the intent of the code, and design documentation should be much more on why the code looks the way it does than on how the code looks. Hey, if I want to know how the code looks, nothing better to tell me how the code looks than the code itself. But if I want to know why the code looks the way it does, that's what the design documentation should be focusing more on. And so let me summarize key points here, and we'll go over to questions. But mainstream projects do perform quite poorly. 18% fail to deliver anything at all. At the point they get canceled, they're over budget by, on average, about 200%. Of projects that do deliver, they're over budget, they're over schedule, they under deliver, and there's a whole bunch of defects in the code. The top 5 root causes, again, in my experience, I have data to support vague, ambiguous, incomplete requirements. 44% of organizations rank that as number 1. About 38% are ranking inadequate project management as being the number 2. The other 3, uncontrolled design code complexity, overdependence on testing, and self-documenting code being a myth. These are my professional opinion, but I think over 43 years, I think that's a well-founded opinion. We can address these top 5 root causes. It's certainly something that's solvable. Here are the references for the things that were referenced. So what I'd like to do now is turn it over to Eric and Jesse, and if any questions came in during the through the chat, then they can forward those to me, and let's see about answering them. So Jesse, Eric, what do you got?
They did. We've got some good ones. Maybe for the first one, it would be helpful for you to scroll back to the key points just a couple before this. All right, that one.
Sorry.
No, just the final one. There you go. Perfect.
Okay.
First question is whether or not for this presentation there's been an underlying assumption of a waterfall process. And in my answer to that, in the chat, I said there's certainly no assumption of an agile process, and we see a lot of people writing systems in a predominantly sequential way. So I said I'd let you weigh in on that too.
Okay, and so the answer is that for the data that I have 20 some odd years ago, yeah, a vast majority of those projects were waterfall-y, plan-based projects, but clearly over time there's been a shift to agile, and so the more recent data is definitely out of agile projects, and so the data that I have is a mix of both agile and non-agile. And the important point that I need to make here is that the data has not really changed significantly, and I will point out specifically that when I was talking about that rework data, those 5 organizations, that rework data, those were all agile organizations. None of them were waterfall organizations.
Right. And I think that's why this slide makes an excellent backdrop for this, because attendees and those who ask this question, ask yourselves, which of these 5 root causes are endemically made better by Agile? Sometimes maybe the incomplete requirements. If you've got a good iterative incremental process where you're testing understanding, your example of a 1.5 years in the dark, followed by an atrocious rollout, right? That shouldn't happen no matter what. That's terrible methods.
Well, I would put it this way. In terms of project management, I think Agile out of the box has some, I mean, we are seeing some improvement in project management. Agile being a easier process to adopt for many organizations. The point is that, yeah, going Agile will help on the project management dimension. But what in Agile, other than bringing in acceptance test-driven development, which most organizations don't, what is it in Agile that gets around the The natural language requirements. Agile projects are just as bad at uncontrolled design and code complexity. If you're trying to test the quality in, et cetera, that nothing in Agile hits the 4 remaining causes. Yes, it can help in the project management, and congratulations there, but it pretty much leaves the other ones untouched.
Yeah. Second one is actually you owe me $1 because the very first question that came in said, "What are those devices over your shoulder?"
I'll pay you in beer, not dollars.
That'll work.
Yeah. Okay. And so over my shoulder are 2 devices. This one right here is a Digital Equipment Corporation PDP-8. 8E computer. It is the very first computer I ever programmed, not just the first kind of computer, but the very first computer. It was at the high school that I went to in 1975. I bought it from the high school and I've kept it ever since as sort of a sentimental thing. It's a DEC PDP-8, and if anybody ever saw the movie War Games, the IMSI 8080 that was there, this is a clone of an IMSI 8080. It's actually an ESP32 processor on the inside. There's a guy in Australia who sells a kit that it's correct size, width, and height, but the depth of the box is actually only a couple of inches, where the real IMSI 8080 is 20 or 25 or so inches deep. But it behaves, it emulates this IMSI 8080, and it's rather interesting for me to be applying the kind of things that we were talking about in terms of modern coding practices to assembly code in the 8080 and assembly code in the PDP-8, et cetera. It's a side hobby of mine to be applying what we know today about coding to these ancient computer architectures and see what happens to the code. It's quite interesting. Another question?
Yeah, the last one, we have 4 minutes. I don't know if that's enough. Can you describe a little more about why you use defect rather than bug?
Yeah, I don't think we're restricted to running over the 60 minutes, by the way. But yeah, the real quick answer here is the word bug is too cute. Oh, my code has a bug in it. Yeah. It's easy to pass it off when we use the word bug. The word defect is getting really at the seriousness here. The code is broken. There is a problem, and we oversimplify things by using the word bug. It takes away the teeth of what's really going on here. And in fact, a consultant buddy of mine, Myler Page Jones, says, don't call them bugs. Don't call them defects, call them what they really are, and that's developer malpractice.
Yeah, and I'm also fond of the IEEE's distinction between a defect and a fault. So they're defects until they're discovered, and then they're faults. So.
Okay, yeah. I read the definition of the defect is the manifestation. It's the observed phenomenon that shows you something wrong. The fault is what is wrong with the code that causes that visible manifestation. But
those are much better terms than bug.
Yeah, sure. We should be using that terminology instead of bug, because bug just glosses.
Well, now every time somebody says bug, we need to see this ridiculous, hideous, ugly, ferocious spider, not some cutesy little ladybug or something.
Well, on a different slide that I didn't include in this presentation, I actually have, I looked on the web to find the grossest cockroach photo I could find. Yeah, and I think it effectively communicates. But yes, don't use the word bug. It's too cute.
So then time for one more quick question. Do you think, is there any evidence so far, or your own professional opinion, whether the shift to cloud has had any influence on things like defect frequency or cost to fix, or is it just more of the same?
It's more of the same. I mean, cloud is a new technology, microservices is an approach, but we always had vague, ambiguous, incomplete requirements before the cloud, and we still have them now. After the cloud, we still have problems with project management. This laundry list, the cloud does not affect this laundry list of problems.
Okay. Well, that's about all that's come through the chat.
Okay. So thanks, Eric. Thanks, Jesse, for the help. And I guess we can wrap this up. And thanks to all the attendees for taking the time out of your busy day to attend. And thanks, and we'll talk to you later. Bye.